Here we go. Okay, so everything started with basically the advent of turbo engines, and especially the turbojets like the 727 that I show at the top left of this slide. And everything was dominated basically by the jet noise, the noise coming from the single stream turbo engines. And the first, I would say, one of the first major breakthrough was actually proposed by Sir James Lighthill that came up with the acoustic analogy that I'm showing at the bottom, which is basically recasting the Navier-Stokes equation into a wave equation, where you separate basically the complex turbulent flow where you have the sources, which will basically simulate it on the right-hand side of the wave equation, to do the propagation zone, which is on the left-hand side of this equation. And that was, I think, the major breakthrough that helped basically scale and estimate jet noise at the time. But even if Sir James Lighthill was a more theoretician, in 1992, in a seminar that he gave, I think at an ICASI symposium, foresaw basically the dawn of a second golden age in aeroacoustics that was enabled by computer simulations. And indeed, I would say 10 years later, in two reviews, one in the Progress of Aerospace Science by Colonius and Lele, and the second one in the Annual Review of Fluid Mechanics by Wang et al., showed that the first CAA application and also the potential of LES, so large eddy simulation for noise prediction. Yet at the time, only simple canonical problems were tackled. Okay, and I'm showing basically one at the bottom left, which is like a shear layer simulation. Then at the top right, a forced jet without nozzles. And then the first, I would say, wall-bounded case, a slanted flat plate trailing edge computed by Meng Wang. 10 years later, again, another review, this time proposed by Lele and Nichols, they basically confirm Lighthill's statement. And at the time, they mentioned actually that we had reached the second golden age of aeroacoustics. And they mentioned that the progression was actually from simple idealized configuration that were isolating specific and steady flow processes. We're moving to more complex flow problem with realistic geometry. And they also mentioned that greater fidelity in capturing a range of turbulent flow scales and thus the noise generation processes associated with them was also apparent. And basically what I'm going to show today is examples of that, okay, and where we have moved actually from that. And we can basically distinguish two types of problems where we have vortices colliding, which is like the free flow cases, which will be represented by jets, or the case of turbulent eddies impacting on solid walls. And actually, aeroacoustic is all about shaking the turbulent eddies. Now, how do we simulate that? These are sort of a sketch of all the numerical methods for noise prediction. And to illustrate that, I'm basically splitting the problem in three steps, which is sketched on the left, where the first step is basically defining the excitation, which could be either acoustic or vortical. Then you can simulate basically or model the response of the blade. And this will be the unsteady loading on the blade, which are equivalent dipoles that can then be fed into some analytical or acoustic analogy to get the far field sound. Now, all these steps can be analytical, and that will be basically the cheapest way of getting the far field noise. Or you can even provide some of the data, some of the input data from classical CFD solvers performing RAN simulations. Now, all of this analytical approach, it's cheap, but it's only for simple source mechanisms and very simple geometry. Actually, we always deal with flat plates, infinitely thin flat plates. Now, if you want to move to more complex source geometries, we can now start using classical CFD solvers, but on the actual geometry, okay? And then we feed that to some acoustic analogy to get the far field. This is fine. This is a little bit more expensive because now you need to resolve the source region, but you cannot really capture basically any feedback loop mechanisms. And also you have a strong assumption on the propagation. You don't account for complex installation effects. Now, of course, the Holy Grail is basically modeling the 3 steps directly. This is good because then you can really model all the phenomena. But now you need to use high order schemes, and still you're usually limited to the near field. You cannot really propagate the whole thing to the far field. And of course, there is a significant increase of the computational cost. All these ideas are basically summarized in the review by Wang et al. In the annual review of fluid mechanics. Now, going into the possible computational aeroacoustics methods. So now we want to sort of simulate the acoustic sources either in free flow for jets or on solid walls. And we want to do some possible coupling, as I said, with an acoustic energy for the far field propagation. The simplest way, if we are interested in deterministic problems, will be basically unsteady RANs, where you basically compute the unsteady mean flow field, but with turbulence modeling. So you don't resolve any of the turbulence. Everything is modelable. Now, one thing that is important if you want to do a CAA problem, you need to have still low dispersion and low dissipation schemes. This is needed. And this will provide basically some tonal noise. Now, if we are interested, because we know that in most problems, it's not only a tonal noise problem, but also a broadband noise problem. If we want to resolve the turbulence, we have 2 options. Either we can use large eddy simulation, where we basically resolve only the large eddies and we model the small ones, or we resolve everything, which is the direct numerical simulation. Now, there we have 2 options. One is using basically the lattice Boltzmann method, which will be very efficient, as we will show, for low Mach number flows, because we use a very compact stencil for it. And again, we will benefit from low dispersion and low dissipation for the acoustic propagation, or we need that. And the alternative is Navier-Stokes solvers, but there you need to use high order schemes to be able to achieve these low dispersion and low dissipation properties. This method I will show is quite efficient for high Mach numbers and high Reynolds number flows. And both of these approaches, lattice Boltzmann and Navier-Stokes, can basically provide a tonal and wideband noise. Now, for complex geometries and flows, which is really the main focus of nowadays, 2 methods have emerged as good solution. One is the unstructured high-order Navier-Stokes solvers, and I will give examples with the AVBP solver, and the lattice Boltzmann method with Cartesian grids and immersed boundary conditions. And I will give examples with power flow. Now, I mentioned in all these CAA methods, we need to have low dispersion and low dissipation, which are 2 properties required for a CAA problem. And here I'm comparing basically the Navier-Stokes, classical Navier-Stokes finite difference schemes with the lattice Boltzmann method. On the left, I'm showing basically the dissipation properties. And you see that the LBM is better, actually, or equal to the 6th order Navier-Stokes finite difference scheme. And in terms of dispersion on the right, it's equivalent to basically a 3rd order scheme. So the other thing that I want to insist on, not only you need these properties for the schemes to be able to simulate properly the noise sources and propagate them, but you need also to have the proper boundary conditions. And for that, you need to have non-reflecting boundary conditions, like the Navier-Stokes characteristic boundary conditions or the radiative boundary conditions developed by TAM. Or you use basically absorbing, so a perfect matching layer boundary conditions, which are absorption sponges, basically, to absorb acoustic. So you need that. Now, let's get into some of the applications, starting basically with the first case where we have just colliding turbulent eddies, so free flow, and I will consider basically jet noise, which historically has been, I would say, the main workhorse in aeroacoustics. Now, what we're able to do nowadays is basically to simulate cold and hot jets with nozzles. And I'm going to illustrate that on 2 different nozzles, one strongly convergent, the RN2 nozzle from NASA, and the slowly converging nozzle from Gene, that was tested at P prime in Poitiers. And I'm showing basically at the bottom some of these unstructured grids. And one particular feature that we've been developing is to be able to do automatic tripping by removing some of the grid cells near the nozzle exit, which I will call basically an industrial tripping device. And to be able to evaluate how we perform, I'm going to look at not only on the center line of the nozzle, of the jet, sorry, but also on the lip line, which is the critical one, and also the radial evolution of this jet. So first starting on the center line, top left, and I'm comparing basically the mean flow along the center line on the left, and then the RMS on the right. The symbols and the black line represent basically bridges experimental data, and the pink squares represent the experiment from Jordan, so from P prime. And in red, you see that we are capturing now really the potential core quite well. And that's actually a significant improvement even compared to the first, I would say, LES simulation that Bodoni performed in his PhD. And you see also comparing the red and the dash blue, the difference between a hot and a cold jet. Now, in terms of RMS, we see that we are also capturing quite well the evolution of the RMS and especially the peak. Now, on the more critical lip line at the bottom, we see that we capture also the mean flow quite well, the evolution, comparing to Bridges' experiment, and also the RMS. So now we are also able basically to capture the evolution along the lip line. And in terms of radial evolution, so here I'm comparing only to the P prime experiment, and I'm comparing basically all the RMS values for the three velocity component. And you see that we're actually matching quite well the evolution and the ratio between the different components. So overall, we have good flow statistics on both centerline and lip line, and we have excellent radial and streamwise development of all jets. Now, what about the acoustics? And here I'm comparing basically spectra at three different angles with respect to the jet axis, and also the overall sound pressure level as a function of this angle. Now you see that for the three different angles, we are actually comparing very well with the P prime experiment. And you see also the difference between the hot and the cold jet. Now, in terms of overall sound pressure level evolution, in terms of the angle, we see also that we are matching quite well with all the experiments from Jordan, Bridges, and Tanner. And again, there is quite a significant improvement compared to the first LES by Bodoni. Now, this is for single stream jets, subsonic ones. What about supersonic jets? And here I'm comparing another simulation we performed on an under-expanding supersonic jet that was tested at École Centrale de Lyon, so at the LMFA lab, and also at VKI, by the way. And I'm comparing on the left the flow field, so the evolution of the mean Mach number along the axis, and the level of URMS also along the axis. And a center line and lip line, and you see that we capture very well the cells, the shock cells, and we also perform, I would say we achieve a better comparison with the experiment, especially for the latest shock cells, and also our capture of the lip line is much better. And now on the right, you see the acoustic prediction for all different angles, and you see that we match very well, actually, the LMFA experiment, except that because of the tripping, we don't have the tones, so we don't simulate the screech, but we have the broadband captured very well. Now, moving to the, I would say, the realistic, very realistic one where we compute the dual stream jet with nozzles. And here I'm comparing with the ExitJet test that was performed at Onera, which is scale version of the afterbody of the CFM56. On the left, you see that the AVBP simulations are comparing quite well to the PIV measurements performed at CEPRA 19, sorry. And on the right, you see also the sound pressure level as a function of Strouhal number. And you see that with increasing grid resolution, we capture basically the high frequency very well. So we have good flow and far field acoustic pressure predictions, and with this industrial tripping method. Now, where do we go from there? Now, there's a trend to move towards fully installed jet noise, and here I'm showing actually some comparisons that we perform with the LBM VLES capability of power flow, where you see the interaction of the jet flow with the plate, and the comparison on the right of the SPL at 90 degrees with the experiment performed at NASA by Brown. And you see that actually the power flow simulation is also capturing quite well the sound pressure level evolution as a function of Strouhal number. And then a more realistic comparison where there is a high lift put actually above the jet. And again, we get like very good, I think, prediction and accurate description of the interaction. And these are all simulation performed by Rego et al. Now, moving to the second case, where we have an interaction of turbulence eddies with wall. The canonical model for that canonical problem is the airfoil noise first. And in this case, we actually try to simulate what happens in actual open jet wind tunnels. And I'm showing on the right our wind tunnel at the Université de Sherbrooke. And on the left, I'm showing a typical instrumented mock-up, and this is the controlled diffusion airfoil that I've been using for many years, and I will be comparing to that. And the trend basically since 2012 has been to move towards more DNS cases and fully installed configuration to also sort of understand what's going on in the experiment. Now, this is what I mean by installed configuration. This is basically the lattice Boltzmann setup that we use, where we basically place the airfoil in the potential core of the jet. We simulate the nozzle lips here, and this is basically the École Centrale de Lyon setup, so with a little contraction in one side. If you do that, actually, you're able to capture quite well the loading on the airfoil. If you do free flow computation, you don't, okay? And you see that it's comparing actually all this simulation, high fidelity simulation, so large AD and DNS are comparing quite well actually with the experiment. The only differences are mainly in the laminar separation bubble that is developing at the leading edge that we see actually in the animation at the bottom. And you see that only the DNS are actually able to capture the size of this bubble quite well, and also the consequent favorable pressure gradient region that you have in the front of the airfoil. Now, in terms of features, as I mentioned, we have this very thin laminar separation bubble that develops. You have these rollers that will form, that will eventually break down, and then you have a forest of hairpin vortices developing along the blade with an angle that will be increased due to the APG zone near the trailing edge. Now, on the right, I'm showing also in the background in gray the dilatation field, and you see that actually for this particular airfoil, the self noise is not only trailing edge noise, but you have also an additional source coming from the laminar separation bubble, and also another one that is developing actually in the wake. Now, if we consider the other cases, so the LES Navier-Stokes with AVBP, we get basically the same sources, okay? And you see also the same thing with power flow. Now, if we compare to some experimental measurements of the noise of the far field noise spectra, you see that now we're able, actually with this high fidelity simulation, to capture quite well actually the trend. And as I said, we now have, because we have this installation, we also see the diffraction at the nozzle lips very well. We also see the sort of cardioid shape due to the non-compact trailing edge sources. And then we have these extra noise sources due to the laminar separation bubble and the wake. This was at design, so at 8 degrees. Now, if we move to a lower angle of attack, experimentally, we saw that we were getting some tonal noise, and especially at 5 degrees, we had some very intermittent, so highly modulated tonal noise. And we performed basically the simulation of this case, and we were able basically to explain why we, and you can see in the background, actually this tonal noise generated with the fading colors, showing that basically this is actually a tone that varies in time. And we were able to explain basically this phenomena with the DNS, where we showed that we had a sequence of quiet events and intense events near the trailing edge that were due to these rollers that were either small, smooth, and not very energetic, or big, strong, and creating basically a strong breakdown near the trailing edge. And that's basically creating this laminar boundary layer instability noise. And basically the main source that we found was the Kelvin-Helmholtz instability that was developing in the laminar separation bubble that is situated actually close to the trailing edge at this particular angle of attack. Now, these rollers were actually verified experimentally by Tomo PIV, where we basically showed that we had these big structures and confirmed basically the LBM, the DNS LBM results. Now, we also perform some noise control simulations with serrated trailing edges, and you see basically that with this three-dimensional serration, we didn't have a change of the loading, so everything is basically similar to the baseline, the clean case. But then in terms of acoustics, you see that actually there is a noise reduction that I'm showing here in the experiment, and you see that we are basically able to capture that either with direct probes in the far field near where the microphones are, or using the Fox-Williams and Harkins simulation. So you're comparing basically the blue lines with the red lines. And you see that we have this significant noise reduction between 1 kilohertz and 4 kilohertz. So in the mid-frequency range where the trailing edge noise is dominant. Now, where do we go from that? Now we are actually moving, I would say, towards higher angle of attack and Reynolds number. And I'm showing here an example that was performed in 2022 by Jacob Turner and Kim, where they perform basically this very high angle of attack DNS, but it's still at a quite low Reynolds number. So I think the trend will be to increase the Reynolds number and also consider more high angle of attack. Now moving to a more complex case, airframe noise. We did first a full simulation of a simplified high lift device where you have basically a flat plate with a flap, which is a NACA 12 airfoils with different positions. And we basically simulated, that was part of a EU project called Valiant. And some of the experiments were performed at École Centrale de Lyon. And that's basically the configuration we've been simulating with AVBP. And you see basically the evolution of the flow field and also of the acoustic field. So this is again dilatation field contours. And what we showed is that we were able to have good flow statistics and far field with AVBP. We showed that we had a strong influence of the jet shear layers here, because you see that there is like a sort of a change of orientation, so refraction through the shear layers. And then we have also diffractions coming from the nozzle lips. And all of this will create the oblique fringes that we see actually in the experiment. And then the other thing that we explained was basically some of we saw some evidence of laminar boundary layer instability noise on the flap because of the low Reynolds number of this guy. And that was actually shown also experimentally. And then we moved to landing gear noise. Okay, and for that we considered all the configuration, the lagoon configuration, which are basically, I think, the A320 landing gear, front landing gear. that we tested again in CEPRA 19, sorry, at Onera. And I'm showing here only the simulation of the Lagoon 1 configuration. And at the bottom, you see that we simulate the flow is quite close to the PIV measurements. And on the right, you see that the wall pressure fluctuations measured basically on the wheel with coolites is also predicted quite well as soon as we move to fine or very fine grids. And similarly, in the far field, we're able to, at the bottom right, able to predict basically the far field noise. Now, with this simulation, not only we have good flow and far field noise prediction, but we were also able to show that we had a ram cavity resonance that was actually found simultaneously also by Casalino et al. With the lattice Boltzmann. So we had the two approaches basically converging to the same conclusions. And they explain the tones that we saw. Now, where do we go from that? Again, I think we're going to move towards full aircraft certification and footprint. And actually, in 2019, Damiano Casalino showed in his keynote that that's already the case for some of, I would say, full aircraft simulation that I'm showing here. Now, moving to the more complex rotating cases, rotating machine cases, and starting with the low-speed fan noise. And for this, we usually simulate configuration of the fan as it is tested, which is usually flush mounted in a board or mounted on some module, as shown at the bottom right. So I'm going to show some examples of these two. First, the fan alone case, and we've been using a test case, which is called the H380 EC1 fan case, where we have a lot of data. And I'm showing on the left the performance. So the two dashed line, not dashed, but dotted lines represent basically the spread of the experimental data, both for the pressure rise as a function of flow rate at the top and the torque as a function of volume flow rate at the bottom. Now, if you look closely, the RANs are performing well. So the steady simulation only performing well close to the design point or to the right of the design point, whereas if you want to capture actually the low flow rate, you need to go to unsteady simulation. And the one that are really in the spread of the experiment are actually the turbine resolved simulation. So either the scale adaptive simulation with CFX or the power flow VLES case. Now, this is confirmed also by comparing the detailed velocity statistics in the wake, where we did some hot wire measurements 33 millimeter downstream of the fan. And especially, I think, only the highly resolved simulation and fine simulation were able to capture actually the radial component correctly, and also the RMS value of it, and basically the shape also of it as a function of radius. So good overall performance agreement, better prediction with unsteady SAS and LBM cases. Now, the most, I think, important results that we obtained on this fan was on this fan, we had the issue of having huge subharmonic humps. So this is the blade passing frequency here. The tone that is emerging, and the other in front of it, you see that you have these huge subharmonic humps, and we have three of them, okay, that are sort of a harmonic of the first one. So in black is basically the experiment, and you see in colors all the other results from the lattice Boltzmann simulation, coupled with the Fox-Holmes-Hawkins analogy for all the cases in blue, green, and brown. In red, it's the direct simulation, and you see that at the low frequency, we have some extra tones here, and this is due to the fact that we have this mass flow extraction. So these are duct modes that are actually excited at the outlet. So this is a spurious effect of the simulation. But you see that all our simulation, either in the direct case or in the acoustic analogy, are now predicting quite well actually the three humps. And we were able to basically explain these 3 humps by these large coherent structures that are forming in the tip gap that are re-ingested and chopped basically by the blades. So these subharmonic humps are clearly captured and caused by the tip coherent structures that are formed. Now, one other thing I forgot to say is that also we showed that the blade is really the dominant contributor compared to the hub and the ring. Now, this has been found also in other cases, and I'm showing here a more recent simulation we did on some urban air mobility ducted fan configuration that you see on the top left, tested in our anechoic tunnel. And you see at the bottom the prediction, the sound pressure level, so the noise spectra comparison between experiment in red and purple, compare basically to all the LBM. And you see that we are actually able to capture quite well all the phenomena. And again, we capture quite well also the subharmonic humps that we're forming on this fan. And we then explain that by the tip vortices, both the tip leakage and the tip separation vortices that stay in the rotational plane and that are creating this intense wall pressure fluctuation at the tip and creating consequently these large subharmonic humps. Now, another case, a little bit more, I would say, odd, not aerospace this time, which is the vertical axis wind turbines. We simulated basically the experiments that were performed at IPAT in Erlangen Universität by, actually, not by Kromer, mistake. And here I'm showing basically 2 cases, okay, the deep stall configuration, so where we have a very low efficiency and a very low power coefficient, and the max efficiency case where we have the highest power coefficient. And you see that we have a very different flow topology. In the deep stall, we have all these vortices that are basically impacting on the mast and on the consequent blade that are sort of re-ingested, whereas at max efficiency, everything is basically triggered by impact on the side plates. And you see at the bottom, basically the comparisons of the noise spectra again for these 2 configuration. And you see that the Lattice-Boltzmann method is capturing quite well. So either with the Fox-Williamson-Hawkins analogy in blue or the direct probe in gray, we are basically capturing the black experimental spectra for both cases. So we get good noise prediction, and again, this allowed also to have a good source localization. Okay, to conclude this part, we've done a systematic also comparison on this H380 C1 fan, where we moved actually from a single fan simulation to a fan system and then a fan system plus a rotating obstruction. So we are getting more and more complex cases. And I'm showing on the right all the simulation we performed with different flow solvers, the grid size also, and more importantly, the time of this simulation, so the duration of this simulation. And you see that for the fan itself, all the unsteady simulation are the same order of magnitude, okay? And except, of course, the RANS, but the RANS doesn't give you the noise directly. But all the others are the same order of magnitude for the same number of revolutions of the fan. But as soon as we move on to fan system and more drastically, I would say the fan system plus rotating obstruction, we start having quite a big difference as we see that the LBM with the fan system is sort of a 1 order of magnitude, so 10 times faster than the URANs, and then we get even 2 orders of magnitude in the case where we consider also these 2 rotating systems. So, and this is, I think, for low speed application, an increasing advantage of the Lattice-Boltzmann method over the classical Navier-Stokes with system complexity. Now, this is for low speed machines. If we move to high speed machines, the first case we consider was a compressor, the low pressure compressor CME2. And I'm showing here on the left the large eddy simulation we performed on a smaller span configuration, and on the right the URANs we perform on the complete stage. And we were basically, with this configuration, we didn't have any experimental data, but we showed some technological effects on tonal noise with the URANs, especially the effect of viscosity, thickness, and camber, so that we could estimate the validity of our analytical models. And also we showed the critical role of the span-wise coherence length in the broadband noise. And by the way, it was also surprising to see that actually transition was only occurring at mid-chord, and especially on the stators, and not really at the leading edge as we were expecting before. Now, the second case was a high-pressure turbine case, which is the MT1 transonic turbine from Oxford. And we did there both clean inflow and also inflow with some planar entropy waves. So this is the clean inflow at the bottom left. This is the entropy wave case on the right. And you see that in this HP turbine case, we have a very complex flows with several shock waves, vortex shedding. So a lot of possible noise sources that we looked at. And we especially showed by comparing the entropy case, wave case, and the clean case, that indirect combustion noise is produced mostly in the first HP turbine row, because everything afterwards, the entropy is completely, I would say, smeared. And then we also showed that we have weak reflection towards the combustion chamber, which is also a very good news, but that was a result that came out of this study. Now, moving to the turbofan case, and we started with the NASA SDT fan, which is an AIAA benchmark, and we started actually with the reference case, which involves 54 straight stators, and we considered the approach condition first, where we don't have shocks. In the initial rotor stator simulation, to limit basically the size of the grid, we sort of rescaled the stator a bit to have a 2-rotor, 5-stator configuration. And you see also the setup on the right with the 2 overset grids around the rotor. And at the bottom, you see the overall performance comparison with experiment, both with RANs and LES. Bear in mind that we have a cold geometry here, and there are some uncertainty, I would say, in the geometry, which may explain that maybe these figures can be found a little bit high, but they are at least consistent with all the different simulations that have been performed, especially at the same time, there were also LBM simulation by Casalino et al., and they basically show the same kind of results, okay? Now moving to more detailed flow comparison. At the top, we are comparing the mean Mach number halfway between the rotor and the OGV. And you see that on the left, this is the hot wire measurements, in the middle, the RANs, and on the right, the LES. And you see that we are actually capturing better the shape of the wakes with the LES, and we are matching quite well, except maybe in the tip clearance. And this is probably due to the fact that we have a cold configuration here. And this is exactly the same thing that we can say about the RMS velocity components. So radial on the left, azimuthal in the center, and the axial on the right. And bottom, the LES is comparing quite well to the top hot wire case. Now moving to the acoustic comparison. So at the top, I'm showing the comparisons performed with 2 different acoustic analogy, the free field Fox-Williams and Hawkins, and then the duct analogy, the Goldstein analogy in red. And we're comparing basically with all the measurements performed in NASA. So in black, this is the OGV alone, actually the OGV noise, so subtraction basically of the full stage, which is in gray, and the dotted line is rotor alone. So we should compare basically to the full stage, and you see that we are comparing quite well for the high frequency part. We only have this over prediction at low frequency, and especially we have additional humps that we believe were due to the 2 large coherent structures that were developed in the tip gap where we didn't have a very strong resolution. And this was later confirmed by performing rotor alone configuration where we achieved well-resolved LES. And you see that the red wall resolved ADS is now matching much better the rotor alone measurements, and we no longer have these extra humps or quasi-tones that we found before. So now we have a good overall prediction using this Gaussian annular duct analogy. Now, where do we go from there? Actually, first, we then perform the same thing for the cutback case. And I will go quickly on this because it's already, I think, 40 minutes. And we are comparing, again, quite well with the experiment. And we were showing that we were able to resolve also the tip leakage flow and the interaction with the blade. Now, where did we go from that? I think the most recent achievement has been to perform full 360 LES, and this was performed by Jean Lam at École Centrale de Lyon on the ECL5 configuration, and I'm showing here a sort of an animation of this simulation. And this was basically providing the full modal acoustic structure, and we showed that there was no significant correlation at high frequency. Now, I would say the final case that I will show is the very recent full engine noise simulation that was performed at Surfax, where basically they simulate with wall model large eddy simulation the full D-gen engine. And you see basically everything is resolved with large eddy simulation, the combustion chamber, the axial turbo fans, and also the centrifugal HP centrifugal fan. So this is basically the new frontier in CAA with couple stages. Now, the thing that we learned actually from this simulation, one thing that was measured at NASA is that upstream they found some blade passing frequency that they were not expecting, that were not corresponding actually to the turbofan. And this simulation showed basically that it's actually a coupling with the HP centrifugal fan. And these are basically acoustic pressures that are coming from this centrifugal fan going through the axial fan stage, and that you basically capture in point A. So significant effect of the coupling at certain line, and only by this full simulation you can get it. So in conclusion, several CAA results in complex geometry have been achieved, combining both hybrid and direct noise simulation. And I hope I convinced you that the third golden age has started. So a very exciting time, I think, for CAA. We're able to simulate more complex and realistic geometries, and especially with the lattice-Boltzmann method. The high order scheme on unstructured grid also provide excellent results for all type of jets, and now also high-speed turbo machines and open rotors. New physics has been unveiled, and common noises found from airfoil to low speed, which bring new insight, I think, also into high-speed turbo machines. Now, where do we go from there? So the perspective, we should tackle, I think, new and more complicated problems. I think the fourth golden age should be something like aeroacoustic elasticity problems. We should continue to provide new insight in noise mechanisms and source localization in different configuration. And we should also develop new analytical models based on these simulations to be integrated in early design. And then, of course, you should compare with new test data that are becoming available, like the ECL5, also the configuration at Leibniz Universitat of Hannover. Now, one thing may be more controversial. I think maybe the next revolution will be also to replace the classical solvers with physics-informed neural networks. Thank you very much for your attention.